Hi everybody, I'm Vadim Yanitskiy. Thanks to Harald for the introduction, and today we're gonna talk about Pycrate. It's a framework for declarative protocol definition and data manipulation. You can basically do all weird stuff with weird binary protocols. And before we start talking about Pycrate, I would like to point out some difference between declarative and imperative protocol definition approaches. And once we start talking about Pycrate, I will give an overview of built-in modules, and those are, in particular, should be interesting to all OsmoDevCall developers, because we usually deal with 3GPP protocols, and might also be interesting to other people who may know something about ASN1 or maybe CSN1. And I will show the hierarchy of the classes or in the Pycrate framework, and show some examples how to build your own protocol, or how to actually use the API of the Pycrate runtime. And also, as conclusion, I will show some other options, other frameworks for declarative protocol definition. So, just in case not all of us are OsmoDevCall developers, for us those terms are quite, those abbreviations are quite familiar, not surprising, but for some of you who is not aware of this, is some terminology. And so what do we have? We have two options when we define a binary protocol. I will be talking specifically about binary protocols because text protocols are kind of easy, at least easy to read. But when it comes to parsing of text-based protocol, I hate this. So I prefer binary protocols as much as possible. And if you're going to develop your own protocol parser or message generator, you have two options, and one of those is the imperative protocol definition, where you basically use your language constructions and define specific code blocks for specific and individual PDU parts. And this is how we do in most of libosmo projects, and also the same applies to Wireshark. You basically parse your buffer byte by byte, and then decide on what kind of field it is, and so on. And the alternative is a declarative approach, where you have generic code constructions for parsing the common PDU parts, and not maybe surprising for somebody, binary protocols have a lot in common. So most basic elements that you would usually find in every protocol definition is the integers, of course, of different size, of different byte ordering, and PID fields, regular ASCII strings, and some special elements like sequence of repeating elements. This is similar to the ASN1 terminology, where you also have sequence and unions, where you also have CSN1 term for that choice. And the main idea of this approach is to have some framework with all those basic constructs implemented somewhere, and you basically build your protocol on top of it. And where do we already have this is our TCN3 testing infrastructure. We use this domain-specific language to do conformance testing of our programs. And in this repository, you can find a lot of examples of how do we do declarative protocol definition. And other two examples is CSN1 codec in OsmoPCU. That's not our own framework. We basically took it from Wireshark, and Wireshark took it from Ericsson, and we'll talk about it later. And since recently, Harald started to use Python construct, other not related to Pycrate, other framework for declarative definition of files, structure of files on the SIM card. And regarding the benefits and disadvantages of using declarative protocol definition, it's always easy to read the declarative definition, it's easy to understand and write something simple on fly. And a huge benefit here is that one definition usually works for encoding and decoding. You don't need to specify the encoder and decoder functions separately, and with that you have less chances to have bugs and security issues unless your framework itself is kind of vulnerable. So if you fix the framework, you fix all the definitions. And from the downsides of using declarative protocol definition is performance loss, because you basically trust parsing or generating the PDU to your framework that is expecting all kind of elements that it supports. And of course, it's slower than doing like exactly what this particular field in this particular place requires to be done. And sometimes, or maybe oftentimes, you will face limitations of the frameworks. This always happens to me in Titan, and especially with weird 3GPP protocols where you have weird calculations of the field lengths, weird tables with magic numbers. So this is sometimes not easy to implement, but for most of the protocols, declarative approach works just fine. And the opposite, hi Paul, the opposite part, the opposite approach in this case is basically the imperative protocol definition, where it's kind of symmetrical. What's good for the actually for the declarative approach, bad for the imperative approach. Like sometimes you see some spaghetti code and lots of code duplication in imperative code, and you often have to define the separate functions for encoding and decoding, as I already mentioned, and you have to take care of all possible buffer overflows, underruns and overruns. And from the positive sides here is, of course, performance, as I already mentioned, and no limitations. You can implement any weird protocols in C and in other language with this imperative protocol declaration. And the main topic of this talk is, of course, Pycrate. This is a Python framework for manipulating various binary protocols and formats, of course, in declarative way. And the project itself, there are many variants how people want to pronounce it, but this is some quote from the authors of this project. It's Pycrate, bad wine. I really like this humor. And it's nothing to do with wine except that it was developed in France. I also liked it very much. And the project itself is a successor of another project with another interesting name. It's libmich. I think it's like love yourself. And the Pycrate itself is maintained by P1sec, and the latest release was 2 days ago, so it's actively maintained. And for some reason, they still support Python 2. I don't know why, and why would anybody need this, but one strong advantage that I really like is that it requires no dependencies, even for JSON. It somehow handles it internally, I guess. And the only talk that I managed to find about Pycrate is on the bottom, this link, talk in French. And maybe my talk will improve the situation for English speakers. And why Pycrate is so interesting to me personally, and like why would it be interesting to other Osmocom developers or non-Osmocom developers? Well, first of all, because it's Python, and with Python everything can be done quickly, and you can prototype a protocol or quickly test something, quickly parse something, or I had some experience with recently with parsing an unknown protocol. That was also quite useful. And Pycrate itself is a rich library. It contains a lot of modules for multimedia formats like PNG and so on, and for some basic network protocols. And what I find funny is that they even have some Osmocom protocols like GSM TAP or layer 1 control that we use in Osmocom BB to talk to the firmware of Calypso phones. And our control protocol is not yet published, but I'm going to submit it there. That's the protocol for controlling SRS-LTE, the external NAS interface of SRS-LTE, the project from my previous job that we open sourced, and from the other interesting protocols, we also have SS7 protocols. Harald had a presentation about some of them last time. 3GPP protocols like NAS, and even some 5G new protocols and information elements. What I often use is the structures for GSM and GPRS, basically radio resources, information elements. From some other modules that may be interesting is the SIM application toolkit and SIM cards, secure packets over SMS. I'm not sure if I know what is it, but I assume it's related to the transparent data barriers. Another really strong side of Pycrate is the ASN1 compiler and runtime. And unlike the other ASN1 compilers, specifically open source compilers, this one supports packed encoding rules, both aligned and not aligned, and also the normal encoding rules like beer, the basic encoding rules, and I don't remember what DER stands for, but it's also should be similar to beer. And you can find more information on this webpage about the compiler and what's supported, what's not supported, just some highlights. And they also, as a part of the repository, provide precompiled modules for GSM, LTE, and UMTS. Full SS7 protocols that are defined in ASN1 using basic encoding rules. You have UMTS RRC protocol, that's packed encoding rules, that's unaligned, and the other protocols like S1IP, that's the protocol that the base stations in LTE talk to the base station controller, not actually controller, but the MME, as far as I remember. And you can find all the other modules in this directory. It's really a lot of other protocols in there. So maybe if you're looking for something, maybe it's already there. And you don't really need to use compiler. They are already in Python. So you can just load them in your interactive shell and decode or encode messages. And there is also CSN1, which is the 3GPP specific notation to describe eGPRS and GPRS signaling messages. And it's not used in modern technologies, so there is not that much literature about it. But there is a nice website, csn1.info, where you can find a lot of basically information about the syntax. That should be enough for you to start reading the magic tables that you often find in 3GPP documents, and this is how they look like. I'm not gonna go into details, but one interesting detail is that you have the specific notation of low and high bits. It's not really 0 and 1. The actual value depends on position within the octet. And that's the reason was that they wanted to introduce new information elements on top of padding octets. So that's why they came up with this weird syntax. And in Pycrate, there should be some utilities to compile CSN1 declarations, but a a lot of them that you can find on 3GPP websites. They contain lots of mistakes. And Pycrate, at least the developers of Pycrate, they fixed some of them in the code, but the specs are still not fixed as far as I know. And as I already said, it's mostly GPRS specific protocols are defined in CSN1, so the Pycrate also provides all possible GPRS signaling protocols already compiled into Python. So you can basically take them and use. And this is how the basic hierarchy of Pycrate looks like. But I personally don't really like this picture. And this is not how I started with my with learning Pycrate. I actually took a piece of paper and started to draw the class diagram. This is what I ended up with on the right. Maybe not really visible, but on the left I have some explanation of some basic elements. You can always check the wiki. They have quite a detailed description of this hierarchy, and this is essential if you want to develop your own protocols or read other protocol definitions. That's really nice to learn first. So you have the root element, the base of all other constructs, the class called element. So you have some common API in there. Then you have array and sequence for repeating sequence of elements. You have envelope, which represents a complete PDU and contains other elements. Also, from the ASN one, there is a similar element, similar to choice, called alt, which is actually like alternative, and it's similar to envelope. It contains some elements, but only one of them will be in the actual message, depending on some conditions that you declare. And atom is a base class for small atomic types. That you will be using most of the time. So here is a buffer, which is just a sequence of bytes of some length, and with string is actually also a sequence of bytes, just ASCII, and the representation in the framework is different. That's the difference from buffer. And you have all kinds of integers with big and little Indian and all different size. And also you can have bit fields that I forgot to mention here. It's basically uint class. You can specify any possible length and in bits. It's like 1 bit fields or smaller, actually smaller than 8. Anything would work. And in case you want to try something with this nice framework, it's unfortunately not available in the Python's repository, but you can easily install it with pip still. And before you start writing the actual definitions, it's always a good idea to include most of the basic construct elements. And here we have a very simple example of the GIF header, GIF image header. You have those famous GIF 89A in the header. So you also pay attention to the BL argument. This is where you specify the length in bits. That means that the buffer is fixed, and there is a fixed length, and it should be of that size. And here is a bit more complicated example. This is also part of GIF format, and this is logical screen descriptor, one of the first information elements that you would see in a GIF file. And here you have basically the screen size that's defined as 2. I'm sure if the pointer is visible on the screen, like 2 little Indian 2 bytes each. So you have 4 bytes in here, and then you have some flags of 1 bit, 3 bits, 1 bit, 3 bit. So that's basically a bit field. And after that, you have 2 integers of 8 bits, unsigned integers. So that's how you declare protocols, and it's already complete definition, you can actually use it already to decode and encode messages. And here is a bit more complicated example. I think I will zoom out a bit. So this is a simplified example of PNG format, where you also have some kind of header with some signature, some magic bytes in the beginning. This is represented by the buff in the PNG class. And then you have a sequence of chunks. So it's basically repeating sequence of elements that's declared here as PNG chunk. And here you have some interesting magic happening, because one of the downsides of declarative approach is that it cannot exist without the imperative approach. So here in the middle, you have some imperative magic, where you calculate the length automatically, and you also calculate the CRC checksum for each chunk. This is how it looks like. And in this constructor, you can basically reference elements by their indexing in the gen element, but you can also use strings. But I don't know why, maybe because using integer indexes is faster in terms of performance. And here is a GSM tab header that we use in OsmoCon to encapsulate frames and send them to Wireshark. And also we have used this header to send logging information. This is also how it looks like, nothing really special, except that in the beginning you have some fields where you expect some fixed value, and if this value doesn't match, then the parser will abort. And you can also have dictionaries to improve the textual representation of fields when you use the framework, and so on and so on. So this is not that important. And this is how you can basically use this. So if you have it installed on your machine, you basically go to the Python shell, or you write a script, you import the protocol definition, then you create an instance of this GSM tab header, and you can even copy paste bytes from Wireshark and immediately feed them into the parser. And here is what you get. You can get a pretty printed view for the message. In this case, that was a CBCH message. And on which time slot? Time slot 2, right? And you can modify the payload after decoding it. This is what we do. We basically change frame number to another one, and then regenerate the message. And then this is what we get in hex. Quite easy. And given the new found love of Harald with JSON in PySim, I also provide some examples how to use JSON here. You can also do export your PDU to JSON and then import it from JSON. Seems to work fine. And if you call the PDU as a function, you get basically a list of integers. And this is how Pycrate represents your PDU internally. It's basically every bit becomes a byte in Pycrate, and then this is how it works. This is not super optimal, but gives you some freedom in parsing and so on. So regarding the alternatives that we have, the most familiar one is probably Scapy. And I'm not gonna give a lot of details about this framework. We probably all know it anyway. It's the difference from Pycrate is that it's not does not contain as much modules for 3GPP specific protocols as Pycrate. So this is why Pycrate might be more interesting for us. And from my experience reading the source code of Scapy, everything looks so overcomplicated, and like, I don't know what in terms of performance, but it doesn't seem to be like if you are doing something performance critical, Scapy is also not the best option, but at least a little bit better. You also have Python constructs. I recently discovered this framework, and we already started to use it in PySim. Harold implemented some files in declarative approach. And recently I had to work on a new TRXD protocol for our BTS setup, and it's already 3 versions of this protocol. So this time I decided to do it in a declarative approach, and for that I implemented my own framework for that. And the reason is performance. This my version of I just called it Codec Py, and it's really simple. I think it's like 1,000 lines. I'm not sure if it's gonna be available here. Yeah, it's like don't think it makes sense to show the source code. Yeah, but it's very simple, and also provides almost the same elements as you have in Pycrate, just not that much freedom that you get in Pycrate, and not super complicated protocols. You unlikely will be able to implement them with Codec. And there is another popular alternative called Kite struct, and this is like a declarative language, and this is also a compiler for this language that can generate the parser or encoder for some languages that they support. And to me it looks like mostly the web languages, except Java or Lua maybe. And yeah, C doesn't seem to be supported. Maybe they have runtime for that. I didn't check, but to me this project looks overcomplicated, and the runtime is very heavy. If you try to clone the repository, it will take I don't know how many hundreds of megabytes. So that's what I don't like in this project. But here is a little example of again GIF image that I already used in this presentation. It's a very simplified example. I'm not sure if it reads easier than previous examples. I find Python examples easier to read for some reason. Yeah, it's what we also have is TTCN3 and Titan. So TTCN3 is a domain-specific language for testing, and yeah, you can always check nice talks by Harald if you want to learn about this more, or you can also check our testing coverage implementation in OsmoTTCN3 hacks repository. And we specifically use Titan. This is a compiler from Ericsson with Eclipse public license. And this Titan features a raw codec for declarative protocol definition. And it's unfortunately non-standard extensions to TTCN3. But we use it a lot, and this is how GSM tab header would look like in Titan. So it's very similar to C, where you also have structures, but on the bottom you have some specific constructions. That's actually the extensions with the variant. And this is how you calculate lengths of all fields into the HDR len. And you also need to define some declare functions that can do encoding and decoding for you from octet strings. And another example is CSN1 codec in OsmoPCU and in Wireshark. This is also declarative CSN1 codec by Ericsson. And you can use it from C and C++. Mostly for CSN1 only. There are no basic elements actually, I think you can implement simple protocols on top of it, but it's very domain-specific framework, and mostly nice for parsing GPRS signaling, but can also be used for parsing GSM REST octets that we currently implement in an imperative approach in libosmo-core. And also for the mobile station class mark, where the mobile station indicates all possible potentially, actually not potentially, but actually supported features. And this is how Okay, I have a mistake on this slide. Of course, it's not GSM tab header anymore. It's a packet uplink hack or NAC message. So you also have uints, unsigned ints of specific size in here, bit size that's passed as the last argument to the macros. And you have unions, you have padding, and so on. And you can also use external types here. So this is what we have in Osmo PCU, and recently we improved it a lot, introduced more testing coverage and fixed some critical bugs. So now it should work better. And yeah, maybe Paul can talk about this later. And that was actually my short talk about Pycrate.